Etching, share, etching. Participants, okay. So, okay, can you see the slides on the screen? Just in case. Right, good. So we're going to start etching. Okay, etching means removal of material from a substrate, from a chemical, from resist. Okay, so etching is very general, and we're going to look at what etching looks like. Okay, we can etch the resist, we can etch the silicon, we can etch the oxide, we can etch the nitride, we can etch many more. So essentially, it means removal of material. So material too can be range of different materials, and we're going to learn on different approaches, different techniques to do the etching. Okay, certain etching works on certain materials, and some other etching works on some other materials. So there's no like one single etching chemical or method or gas that can etch the whole thing, okay, or a range of different things. So it only works on certain types of material due to certain mechanisms, okay. So let's just recap on what we have learned from the previous topic, lithography. So let's go through question number 1. What are the requirements of a good photoresist? So let's discuss perhaps 3. What are the requirements of a good photoresist? Anyone can write down or have good addition? Cool, right? That's good. Good addition is one. High resolution, perfect. Yes, high resolution. Without high resolution, you won't get good features or good printed patterns. High resolution, satu lagi. Apa lagi? Dia punya requirement banyak lagi, tapi we'll just discuss 3 and then you learn the rest yourself. Good addition, high resolution. Any other? High etch resistance. Yes, you want only certain locations to be etched as intended, and some other locations that not supposed to be etched, not to be etched, right? So high etch resistance. Kalau tak ada high etch resistance, then dia akan etch semua. So that will be very bad, and that will kill the whole patterning that you've done by lithography. Right, done. Explain lithography process. Low defect density, yes. Low defect density, of course. You don't want to have particles in your resist. They can affect the DOF, for example. Okay. So if you learn about DOF, focus, and then how the non-uniform resist coverage could affect the DOF, could affect the focus, that will eventually affect the resolution of the printed patterns in this case. So yeah. Okay, explain lithography process issues related to CD of a printed feature. So what are the issues related to CD of your features? So let's discuss 3 issues. What are the first? Revolving around CD or line width. Okay, CD is line width. Either it's lines or holes. Overexpose, yes, overexpose. That will result in, so if you overexpose, then what do you expect? Let me know. Give example. If overexposed, then lower CD than expected. Okay, if you ask this question, then you have to be able to elaborate, including whether or not you're printing lines, whether you're printing lines or holes, because that would be, the effect would be opposite, right? All right, so any other? Overexposed is one. What's the second one? What's the opposite of overexposed? John, second one? Straightforward, right? Opposite, yeah? What? Underexposed, okay? Underexposed, that will result in opposite to what you expect. Done. Third one. Lagi? can either say overdeveloped or underdeveloped. Or exposed pun sama. Exposed could be another potential issues as well. Okay, exposed, develop. Lagi? Apa lagi? That will affect the CD. Last one. Related to the CD. What are other issues on CD? Who else? Hadi. Fakri Hadi. Apa lagi? Satu lagi issue? Yeah, standing wave, right? Standing wave. What happens? If you get standing wave, then how does it affect the CD? Haziq. Can mute yourself. Can write down as well. So if you have standing wave, so how does it affect the CD?
How it affects CD. But they're not apa tu that word. They're not uniform. So but it happen because of constructive yes, something like constructive wave because of
reflection, yes.
Yes.
Okay, so if you have those ridges, on the vertical patterns on the side walls, so how does it affect the CD then?
It affects CD of the resist by every the ridges actually make it the CD not constant.
Not constant throughout the side wall.
Yes, throughout the side wall.
Okay. Right, thank you. So below you explain issues related to CD, so you have to be able to relate how does underexposed, overexposed, overdeveloped, underdeveloped, standing wave, whatever, goes back to the CD. Jawab sebab soalannya CD kan, so you can give different answers that are around it, but then don't forget to connect to the CD. Kena sebut balik CD tu because kalau tidak dia jadi hanging. Jadi mungkin betul, mungkin tak, depending on how do you relate the two. Okay. Right, standing wave on the sidewall. Okay, already discussed. Standing wave on the sidewall of photoresist is a huge problem in photoresist. How do we solve it? Two solutions. Solution number one, how do we solve standing wave? Belajar je last week kan? So what is the solution number one? What could you do to solve the ridges? You can write down, you can unmute yourself.
AR bug tu.
Okay, letak bug. How does it help? Thank you.
Reduce reflection.
Then, if you reduce reflection,
there will less standing wave.
Okay, you have to relate. Okay, dia punya bug, then less reflection, as a result, less the issue. Okay, constructive and destructive interference on the ridges, and it will smoothen the sidewall. Done. Number two. Solution number two. Anyone? How do you solve standing wave issue? What else can you do other than ARC or BARC? Satu lagi option, if you don't talk about BARC, you can also talk about TARC. So it can be applied. Beneath the resist as BARC bottom, ataupun it can also be applied on top of the resist as TARC top, anti-reflective coating, right? So you may encounter BARC and TARC every now and then. So second solution, anyone? Faris. Right, diffusion. PEB, diffusion during PEB. Okay, how does it help? Alia and Faris, how does diffusion help during the PEB? Alia? If you have diffusion, therefore, ready? So as a result of diffusion, can write down, can unmute yourself. Boleh cakap je. Alia or Faris? Faris, how does it help? Wait, okay, right. Alia? Okay, let me see here. Rearrangement of the overexposed and underexposed PR molecule. Yes, the diffusion of the molecules, they move, okay, the molecules move, and that will smoothen the ridges, the side walls. Hence, lower, or you can eliminate the standing wave, right? Done. The main requirement of the NGL, you can just take EUV as your example, okay? Or properties yang adalah EUV itu will be the NGL thing, okay? Next generation lithography. At least for now, we don't have any other system beyond EUV at the moment. So let's continue with etching. So we have discussed briefly about removing materials, and then we're going to see later on how do we remove the silicon or the oxide, for example. Okay, we discussed about patterning of oxide. Before this, when you talk about lithography, we have discussed up to the patterning of the resist. So that means bila you open the resist, you etch the resist yang soluble, for example, whether it's positive or negative, yang soluble, you open the area and then you'll get something like this, for example. So let's assume this is yang high area ni semua resist. Okay, let's just assume this. PR. Okay, PR remaining. Okay, so this most open area, PR yang removed. PR removed. So if you're talking about positive resist, that means area removed ni will be the area yang soluble lah, area exposed. Okay, so if the resist is being coated on oxide, okay, on a very thin layer of oxide on silicon, then this open area, the open areas money, should be the oxide. Kalau resist is coated on something else, some other material, then that material will be something else. Kita assume it's silicon dioxide. Because say that you have grown a very thin layer of oxide, and then you have done CED, bar lithography, and then you develop, and then there'll be open areas, and there'll be remaining areas of the resist, and those open areas should be silicon dioxide exposed to the environment. Okay. Sekarang ni, if you want to pattern the oxide, if you look at this, for example, the oxide is not yet patterned, right? So the oxide ada je kat bawah tu. Ada kat bawah. Effect kat bawah resist ni pun masih ada oxide, which is part of the other part lah, other layer. So you have like oxide blanket because you've grown through, say, thermal oxidation, and then you close certain areas with resist. That will be a protection layer. So kita akan tengok next, how do we do the etching of the open areas? So what is etching? Etching is a process of removing solid films, generally. So it could be resist, it could be silicon, it could be oxide, it could be nitride, it could be carbide, it could be some other material as well. So when you talk about etching, when you talk about removing materials, it can be done by wet etching. Wet means involving chemicals. Dia akan pakai chemical HF, nitric acid, what else? Etching, potassium hydroxide, TMAH. Semua tu wet etching. Hydrogen peroxide. So involving chemicals, if you talk about dry etching, it involves plasma. So now, what is plasma? What is plasma? Have you learned anything about plasma before at all in your previous courses? Ada. What is ion? Okay. How do you get the ion? Where do they come from? Sebelum ion tu dia apa tu sebenarnya? Plasma is yes, ions. Tapi sebelum dia jadi ion tu dia jadi apa? What? Anyone? Anyone learn about plasma before? Sekarang go bahas satu-satu. Liquid. Right. Plasma usually originates from ionized gases. Gases yang kita dah ionize. For example, argon, Ar, you strip off the valence electrons, then you can form Ar plus. Okay, so Ar plus is the ion. So kalau you ada banyak cloud of Ar plus, then you're going to get plasma, argon plasma. Okay, tapi originally dia datang dalam bentuk gas, argon gas. Tapi you strip off the valence electrons, dia akan jadi argon plasma. You're going to see colors and everything. Right? Tak apa, kita akan tengok nanti when we talk about dry etching. Characterizing etching, isotropicity. When you talk about etching ni apa yang kita guna? UV plasma. Try to check what is the concept behind plasma TV. How does it generate the plasma? Okay, plasma TV ya. Okay, apa tadi? Yeah, okay. The material that you use to remove some other material, either use chemicals or plasma, they are called etchant. Okay, etchant. Kalau let's say you pakai HF to etch silicon dioxide, then HF is the etchant to etch silicon dioxide. Okay, etchant. So kalau gas, then argon gas, then argon gas will be the etchant that will generate the plasma to remove silicon, for example. And when I talk about etchants, there are few parameters of the etchant that you have to understand. For example, isotropicity. So it is characterized by whether it's an isotropic etchant or anisotropic etchant. Okay, isotropic means a non-directional etching. So when you use one isotropic etchants, that means you will, if you have this etchant, katalah ni material you, they can etch in all directions at the same etch rate. And dia akan remove keliling dia sama je rate dia. Dia tak ada sebelah tinggi pada sebelah, semua sama. So that means isotropic etchant. Dia akan etch semua same equal with the same etch rate across. Okay, dia tak ada direction tertentu. So on the other hand, if you talk about anisotropic etchant, it is unidirectional. Dia akan etch material in one direction only. So maksudnya you'll probably get some etching on the side as well, but then the rate will be very, very, very low if you compare to this vertical direction, for example. So at this point, you call this as anisotropic etchant, one direction only. Yang tadi isotropic because it attacks all angles with the same etch rate. Right? So another important parameter is called selectivity, where this relates to the relative rates at which two chemically distinct solid films are etched by an etchant. So dia ada macam ketahanan lah, selectivity ni dia, for example, you want to etch silicon dioxide, and silicon dioxide can only be etched by HF, but it cannot be etched by some other chemicals, for example. Then they are the that's the selectivity, because it only selects certain material to etch itself, ataupun dia will be etched by only specific chemical. So that's called selectivity. Maksudnya kalau letak certain chemical, you letak silicon dioxide in HF, it will be etched. Kalau letak silicon dioxide in water, it will not be etching. Okay, so that's called selectivity. So they're selective towards the etchant. Removal of unwanted material from wafer surface, yes. Pattern etching, for example, the permanent part of the patterning sequence. So it will remove material from selected areas on the wafer that are not protected by the photoresist, just like what you saw in the slide. Okay, kita akan etch nanti silicon dioxide yang exposed, right? Whatever that is protected by the resist, covered by the resist, will not be etched. So that's called pattern etching. So you nak patternkan dia even further. So remember, when you pattern photoresist on your silicon, on the silicon dioxide, on your whatever, photoresist is not a permanent pattern. Resist ni duduk kat situ sebagai intermediate. You have to have pattern resist because you need to pattern something else under the resist. Bukan sebab you nak pattern resist and leave it forever on the chip. So resist will not be there on the chip forever. Kita guna dia sebagai dummy step saja untuk you etch something else. Then eventually the resist will be removed from the system. Kalau you ada resist on the system atas silicon tu, you carry through, then resist tu dia akan react with chamber of the next processes, and that will cause cross contamination. Remember, resist is a polymer, so dia ada stability, ada certain temperatures that it can withstand. So some temperatures outside lithography can go up to say 1000 degrees C, 1001 degrees C. That will definitely damage the resist and cause cross contamination. Okay, so resist will not be there forever. Kita cuma nak dia pada kes untuk kita buat patterning of the next step. So resist is not part of the device. Okay, just an intermediate step ataupun dummy step. Right? Etching can also be unpatterned. That means complete removal of a layer whose purpose is done. So for example, kalau you ada oxide, okay, kat certain area, then you suddenly want to etch the oxide. Then you just go and etch, and there's no patterning at all. So this is called unpatterned etching. So for example, resist, sec ox ataupun sacrificial oxide, nitride to define transitor active areas. So we're going to learn later on. And another form of etching is wafer cleaning. So anyone has done wafer cleaning? Waktu FYP? Pernah cuci you punya device? You punya ni tak? Silicon. Tak ada kot. So if you get through this silicon cleaning, you must have done, at this point, you must have done RCA. Radio, kenapa radio lah tiba-tiba kan? Radio Corporation of America. Radio. So this is a method patented by RCA, Radio Corporation of America, to clean silicon wafers. So it's a method. RCA is a method. Tapi nama dia Radio Corporation of America lah, full name. It's a patented technique that you will use to remove metallic contaminants, organic contaminants, native oxide on silicon wafers before the wafers can go through fabrication processes. So it's wafer cleaning. Wafer cleaning pun involve etching as well. Tapi kita panggil cleaning lah. But then to be able to remove metals, organic, you have to be able to etch those unwanted materials. Okay, that's etching as well. So let's relate to what we have learned before. Basic terminology, right? You have got your silicon here as your substrate, and then say you deposited silicon dioxide. Katakan you dah deposit silicon dioxide as your deposited film. And then you want to pattern silicon dioxide. You don't want to pattern just photoresist. Eventually, you not pattern silicon dioxide, remember, because resist will not be there forever. It'll just serve as an intermediate step for patterning of other layers beneath. Okay, so then you spin coat resist. Okay, you spin coat resist in coating process on the silicon dioxide, and then you go for exposure. You expose these areas are exposed, and then you develop, right? Then you develop the resist. So now, if you develop this resist, is this resist p-type or p-type? Sorry, positive or negative? Look at this step, D, relate to the exposure step. The resist that we use in this case, is it a positive resist or a negative resist? Anyone? Is it a positive resist or negative resist? Revision to lithography. Tengok tu tempat mana dia expose and everything. Anyone? Faris? Haziq, positive. Kenapa positive, Haziq? Amirul, positive. Why is it positive?
Positive, expose, soluble.
Right, positive, expose, soluble. Kan, saya dah pesan kan? Negative, expose, hardened. So in this case, the positive, for this all, sebab dia tak ada resist kat sini, so that means, and that is the exact exposed area, so it's removed already. Therefore, it's a positive resist. So in this case, you have, at this point, you have patterned the resist. Tapi belum pattern oxide lagi. Kan? You tengok oxide kat bawah dia masih blanket, masih full. But then the resist is already patterned. Remember that you want to pattern the layer beneath. Eventually, resist tu cuma intermediate step. Okay? So to be able to pattern the underlying layer, you have to pattern the resist first, because resist is the polymer sensitive, a light sensitive compound, light sensitive polymer. And oxide, for example, is not a light sensitive compound, so therefore it will not react to exposure or non-exposure. So in this case, you have got your resist pattern to be able to etch the open areas. Okay, open area. Macam kita tengok ke Sam tadi. Ni open area ni kita nak remove dia. Kita nak remove lagi dalam. Nak korek lagi dalam sebenarnya. Masuk lagi dalam. So you want to remove those open areas as what you see here. Now remove sini. Remove sini. So then you are actually patterning the oxide in this case, assuming it's oxide. Assuming it's oxide. It can be some other material as well. So lepas pattern oxide, apa kita buat? We remove the resist. Okay? We remove the resist because resist is not supposed to be there on the device. We just want to do the patterning by using the resist as an intermediate step. So if you remove resist, then you are left with pattern silicon dioxide. Done. Okay? So etching of firm and silicon, selectivity here. You can learn a few things here briefly. Selectivity of materials to different etchant in this case, and then directionality, because you can see some direction to this. Kalau tak ada, just imagine if the etching at this step, kalau you etch, this is anisotropic etching, sebab dia one direction, right? What if you use isotropic etching at this step? What do you get on your resist pattern? So not resist pattern, on your oxide. Kalau you pakai isotropic etchant untuk etch this step yang saya bulat ni, how will your oxide look like? Anyone? Go back to this. What do you get here? What do you expect to get? Teka dulu sebelum kita belajar detail ya. Anyone? Any idea?
Oxide tu dia tak bentuk petak macam tu lah. Dia mesti negatif punya. Dia mesti
dia mesti apa? Tak clear ni.
Dia mesti oxide tu dia mesti masuk ke dalam, dia tak petak macam ni.
Oxide akan masuk dalam, right? So oxide tu dia akan masuk dalam macam ni. So negative, I love that word. When you mention negative, that means you understand how the patterning works. Positif, ingatlah kita discuss positif macam tu. Negatif dia masuk dalam. So anything yang masuk dalam, kita panggil dia negatif. Whether it's rounded or masuk macam trapezium ke, still negative. So your oxide will be like that if you use isotropic. In this case, it's anisotropic. So kalau you guna isotropic dekat previous step saya bulat tadi, then you're gonna get your oxide like that. It's curvy, inwards. Side wall you akan jadi macam tu. Side wall masuk dalam. So that's a sign of isotropic etchant being used for etching in the previous step. before you remove the resist. Okay. Right. So clear? Good. So there are a few things that you want to learn: etch rate, selectivity, anisotropy, uniformity, homogeneity. Okay. Saya dah cover sikit tadi. Etch rate dah cover sikit. We're going to look into the details. Selectivity and anisotropy, whether it's one direction or just equal etch rates around. Right, etch rate, speed at which etching occurs, typically nanometer per minute, nanometer per second, angstrom per second, as long as its thickness over time. Okay, it can be micron per minute, it can be micron per hour, it can be nanometer per hour, angstrom per second. There is no fixed unit. As long as berapa banyak you remove, nanometer, over berapa lama it takes. Okay, say nanometer per minute. So for example, if you remove 10 nanometer per minute, per 1 minute, so then the rate will be 10 nanometer per minute. Simple math lah. So kalau you nak 10 nanometer per second, then 10 nanometer over 60 lah, 60 second. So 1 over 6 nanometer per second. Okay, there's no fixed unit. Depending on your products, devices. Kalau you buat micron, you're gonna be talking about micron per minute, micron per hour. Kalau very small region, then perhaps nanometer per minute. A ratio of two etch rates. Okay, S equals selectivity equals to R1 over R2. So two different etch rates. Okay, and then example, silicon dioxide etching with hydrofluoric. Okay, contoh tadi ya, silicon dioxide, kita nak etch silicon dioxide with HF, and this is the equation of the reaction: silicon dioxide plus HF, kita akan dapat H2SiF6 plus 2H2O. So kita akan dapat oxide will then be removed. Okay, determine the etch rate. You can check out yourself how thick of the resist mask. You can check out yourself. Etch rate and selectivity are crucial for defining the mask. Okay, so you need to know how thick your mask, what are the materials needed to be as your mask, and all stuff, right? Okay, exact example yang kita discuss tadi. Anisotropy. Isotropic etching remove material equally in all directions. So that means the etch rate in all directions are the same. As result, kalau you etch, you akan dapat rounded features, just like this, isotropic, macam tadi ya. Okay. On the other hand, if you, this is also called undercut. Kalau masuk fab, dia orang cakap undercut. We see undercut. Undercut maksudnya ni lah. You punya etching tu masuk dalam. Undercut, bawah feature. Undercut, right? So on the other hand, if you etch anisotropically, then it will just etch in one direction, then you will get a vertical wall. But ideally, you won't be getting vertical walls, but you'll be getting near vertical wall. Mungkin positive sikit, mungkin slightly negative. It depends on what you intend to get. But typically, it's a bit positive. Anisotropic etching remove material only one perpendicular to the surface, which is one direction, accurate transfer of mask pattern. So that will actually transfer whatever you have on the mask, on the resist, will be transferred to the underlying layer. Okay, so apa yang ada kat situ, dimension dia exactly will follow. So anisotropic, dia akan remove, dia akan makan dekat betul-betul dinding ya. You can define that. In this case, the resist acts as the mask. Banyak lagi ya material yang boleh guna sebagai mask, but yeah, for this particular case, let's just talk about resist as a mask. But we can also use some other materials as a mask. Anisotropy is defined as vertical etch rate minus horizontal etch rate. So that means when you talk about even one direction, dia ada juga horizontal etch rate. Horizontal component tu masih ada. But then the rate will be very, very small. Okay. So horizontal ni almost maybe negligible lah. Vertical, vertical, if for example, if you take this, A equals vertical minus horizontal per verticals, kalau you simplify, you're gonna get this. Okay, A equals to 1, because vertical over vertical is 1, minus R horizontal over R vertical, right? So if you look at this equation, if your R for horizontal is negligibly small, what do you get as your A? what is the anisotropy or value of anisotropy if your horizontal edge rate is very, very small in comparison to R vertical? What do you get as the value of A? R hor much smaller than R vertical. Yes, A equals 1, right? Okay, A equals 1 because A now equals to 1 over, 1 minus so small over so big. So 1 over 1 minus almost 0. 1 minus 0 is 1. So then the anisotropy of this equation, of this reaction will be 1 or almost 1. Okay. So if you get A equals to 1, that means your etching will just be perpendicular to the surface. Okay. Kalau you punya anisotropy is lower, say 0.7, so that means you also have quite a significant magnitude of your horizontal edge rate, right? In comparison to vertical. Maknanya dia quite significant lah. You cannot simply neglect the horizontal component if your A is 0.7, for example. Kalau tengok si A 0.5, even worse lah. That means the strength of your anisotropy is not so good. That means horizontal punya component sama dengan vertical punya component. So we just manipulate the equation there to understand the mechanism, right? Uniformity, homogeneity. When you talk about uniformity of etching, so we talk about many things. You can talk about uniformity across one wafer. You can talk about uniformity across two different wafers. You can talk about uniformity across 25 wafers, which is in one batch. For example, one cassette ada 25 wafer. Ada 25. So you can also talk about across the wafers within a batch. Or you can also talk about uniformity across different batches. When you pot across pot, across pot, you can also talk about uniformity across this month versus last month, tool A versus tool B, different etching lama versus etching baru, or different production time or something, right? So it can be analyzed in the form of different conditions, okay? Wafer to wafer, multi-wafer processing, across one wafer, you nak compare center dengan edge pun boleh, center dengan edge of different wafer boleh. So thousands of different possibilities when I talk about uniformity, okay? Kadang-kadang you run wafer yang sama, layer yang sama, setting yang sama, CED yang sama, etching yang sama, on different on wafer on the same set of equipment from supplier yang sama, brand yang sama, model yang sama, time yang sama, you get different uniformity. Why is it so? Any idea? Semua sama, tapi keluar lain. It's not that bad, but then it's different. What could be the possibilities that leads to different uniformity? Mungkin you run semua sama, tool A, H, kita tengah H equipment A, H satu lagi batch, H on equipment B, sebelah-sebelah je. The parameters are all exactly the same from the first day, daripada wafer preparation, grinding, polishing, whatever, sampai etching, semua sama sebiji. But then after the etching, the uniformity is slightly different. One is better, one is not so good. What do you think could be the root cause? Ini real issue dalam step. This is not, kalau you learn theory, then this cannot happen at all. It's just impossible, but it's always possible in the actual line. Any guess? Come on, anyone? Let's just finish with this. No, everything is the same, Sakina. Recipe sama, flow rate sama, dispense sama, nozzle sama, wafer sama, oxide sama, resist sama, equipment brand sama, model sama, beli tahun sama, install on the same day, PM sama, uniformity lain. Why? Kita stop kat sini. Tapi let's just answer this first for like 2-3 minutes. Anyone, different recipe? No, not possible because everything is exactly the same except uniformity results. You tengok? Yep.
Artinya
Yes.
ada possibility yang bersalahnya adalah site ataupun resist.
No, In this case, we assume there's no mistake at all. Everything is completely the same, exactly the same. No mistake whatsoever.
No, so maksudnya
Semua
mesin tak
sama.
salah.
Tak ada siapa yang salah. Mesin tak salah, operator tak salah, recipe tak salah. So, in fact, semua sama. Uniformity je tak sama.
Paper
Paper semua sama. Tak ada siapa yang bersalah dalam kes ni.
tapi keluar lain.
Keluar lain. Okay. Saya nak ajar you satu perkataan, tapi you jawab dulu. You dapat perkataan ni, you understand the whole thing. This is very crucial. Takdir Tuhan. Taklah, memang takdir Tuhan. Tapi what is the science behind it? Behind the takdir Tuhan. Yes, takdir Tuhan, of course.
Murphy's Law.
Nah,
Nah,
nope. Anyone, come on. Let's go for 1-2 minutes. It happens, okay? Bila you faham, this is, bila saya ajar subjek ni, it's not only on the theory, saya nak ajar the practical side of it. Bila you dapat perkataan ni, kalau you jadi process engineer atau you masuk intern, you will appreciate many things. You tengok ada beza, and it happens all the time. Solar industry, LED, IC, SSD, it happens all the time. Just the magnitude tu ya akan berbeza from company A to B, equipment to equipment, But then this is the very one word that you have to understand from today's class. Any other guess? One last guess. Semua sama. Dulu saya ingat benda tak logik. Bila saya dah kerja, oh logik punya. And it is called as something. You dah buat semua sama. You dah buat whatever it is. You dah follow exactly the same, but you get something different. So if you, katalah you compare between two different batches. So if you talk about uniformity, that means, for example, kalau kita discuss about CD, CD batch pertama, CD batch kedua. Then to be able to compare, you need to measure the mean, which is the average, and STD, standard deviation. Okay, you can do this on Excel. Okay, try to explore kalau yang belum tahu, simple je. Mean, STD, standard deviation. Kalau you buat ni, you can. These are the typical stats, I say the simple stats that we use to compare performance from between A to B, C to D. Okay, kalau tengok tiba-tiba mean dia sentiasa equipment A sentiasa, if you measure CD, your target say 100 nanometer plus minus 3. Yang you measure on A sentiasa 1 nanometer higher than B, despite whatever you did. Okay, tak ada ni. So the answer is, it's called matching. Matching. So that's the word. Kalau saya tak sure dalam SSD, LED pakai the very same word or not, but the idea is still the same. And for wafer fab, this is what you use, matching. Equipment to equipment matching. Kita dah faham, dia macam behavior equipment lah. You run semua sama, chemical lah, wafer lah, PM lah, whatever you do. This is just a 1 nanometer higher, or 1.5 higher, or 2 nanometer, or 3. So that's called matching. Whatever you did, dia akan tunjuk behavior. Dia punya perangai lah kiranya. So machine ni you akan tengok di process, every machine dia ada dia punya own behavior. And sometimes you as process engineer, you have to match performance by offsetting. You can offset. Kadang-kadang A is higher than B, therefore I need to offset B by say 1 or 2 so that it's always the same. So matching leads to offset. Ni process engineering kind of keyword ataupun equipment engineering. You ada matching, you have to have offset. This biasa ada, kalau you plot A and B, it's always like 1 nanometer, 2 nanometer higher than B on average. So that's called matching. Whatever you did, dia akan macam tu. Kan? So, dan kadang-kadang dia drift, matching drift from time to time. Tapi it won't be so much. But then, you have to appreciate the behavior of the equipment, of the process, when you become equipment engineers or process engineers or quality engineers. Matching will be one inherent parameter that you have to acknowledge. Wujud you buat apa pun sama semua, tapi ada wujud. The magic tu. The magic factor.
Thank
you. Dia akan ada some offset. So you will appreciate this if you get to handle yourself during your internship ataupun your first job later on. So let's just stop here. You learned something from etching today. So we're gonna continue. Sorry, apa? Selasa, right? Okay, Selasa. So we'll continue tomorrow with the remaining. Okay. So any questions so far? Okay, is it okay? Right, all good. Okay, then I'll see you tomorrow. Bye-bye. Assalamualaikum. Stay safe.